Let me just introduce. My name is Manish, as some of you know. I'm the president of OneQuantum Nepal, and I'm also a quantum engineer at IQM Quantum Computers, right? So OneQuantum Nepal is a branch of, or part of OneQuantum, which is our parent, a non-profit initiative. And with this initiative, we aim to promote quantum science and quantum technologies in all around the world, right? Especially in places like Nepal. The main motivation is to bring this technology and make it accessible for everybody. So that is the whole idea. And it is a platform where we provide you guys help. So it is for you guys, right? We want to give you opportunities to learn about this stuffs and this quantum technologies, and provide you with platform where you can network with experts. And we do that with our mentorship program, for example. And I still recommend you guys to join it if you're interested, because you can sign it up until end of April. And other events, which we will host in the future, quantum summits, will bring invited guests and so forth. Now, today I'll teach you a little bit about how to manipulate states of qubit, right? And precise manipulation and fast manipulation is important to maximize, we call it the clock speed of QPU, not CPU, not the regular CPU, right? But it's QPU, which is quantum processing unit. And how do you manipulate qubits, right? And I will talk about manipulating a single qubit, right? But to build a quantum computer, like fully fledged quantum computer, you need like thousands, millions of qubit. But let us start with one qubit, right? And because that's the most simple. So just to recap, I told you what a qubit is, right? And you know what a classical bit is. It's a state of your information processing unit, that it can be in state 0 or 1, right? Nothing in between, right? That is classical bit. And this sort of information processing units, you find it in your laptop, in your smartphone. Some of you are tuning via smartphone. But now with quantum computer, we are talking about quantum bits, and we call it in short qubit. And qubits can be in state 0, 1, and both 0 and 1 at the same time. And that is one of the most important, right, or fundamentally different idea with quantum computers. And they allow you to process information faster, perform your calculation faster, right? You can solve problems on these devices faster, right? Once we have fully fledged quantum computer. Right now it is tiny, and we can still do a lot of cool stuffs on it, but to get real quantum advantage, we need to wait, for example, another 5 years. And this is the right time to learn about it, because then you can still anticipate the technology and be involved and be part of it. So it is the right time, I would say, to get into this technology. So quantum computing architectures, right? So the qubits are fundamental units of different quantum computing architectures, different quantum processors. And I told you in our first talk, there are different candidates for quantum computing and quantum computers rather. And so you see on the left, there is superconducting loops. Companies like Google, IBM, Rigetti, D-Wave, they use superconducting loops or superconducting qubits as their information processing unit. Companies like Honeywell, IonQ, they use trapped ions, which are basically natural ions, right, that you find in nature. They use that as an information processing unit. Intel, for example, they use quantum dots. You can define qubits, right, discrete state on this quantum dots. And more recently, Microsoft, they're investigating this topological qubits, which is completely different, which is very, very different. And they use the topology, right, like to be in this form or that form as 0 and 1. And this is kind of still a little bit not well understood. this one. Let me do a slideshow, full screen. This is not very well understood, and they are still investigating that. But if they can somehow build this, it'll be revolutionary, because topological qubits, they hold promise that the decoherence, which means noise, it'll be almost noise free, right? I'm not an expert in this topological qubits, but from news and just like here and there, I hear that they're still building that, and it doesn't exist right now. But if once they can do that, right, Microsoft, if they can do that, that would be really great. But our focus is superconducting loops, right? And this is what we use as qubits in our company at IQM, and it is made out of simple electrical circuit, right, which has capacitors and inductors. And capacitors store energy in the form of electric field, and inductors, they store energy in the form of magnetic field. So there is really electrical energy and magnetic energy. And if you cool this down to 0 Kelvin, you can actually, this macroscopic huge thing can behave like a quantum particle. This macroscopic circuit behaves as a quantum mechanical system, but you need to cool it down to almost 0 Kelvin, right? And you use dilution refrigerator, and now like this dry fridge, right? More recent, more advanced kind of refrigerator that doesn't use liquid helium. And you need to store this electrical circuit in those extremely low temperature, almost 0 Kelvin, and you can build qubits. Was there a question? No? Okay. Yeah, so that is the whole idea of the superconducting qubits, and these are like one of the most promising candidates. And a lot of companies, big companies, right? IBM, Google, they're working with superconducting qubits. And there is also this ion traps, which are also quite interesting, of course. And it has its own use, and I'm not too familiar with ion traps, but they trap ion, right, in this so-called Pauli trap in thin air, right? And so you define qubits on states of these ions. Ions have these energy levels, and then you can define qubits out of the states of ions, right? And you can manipulate them using lasers, laser fields, right? We manipulate here the superconducting qubits using microwave pulses that are in the microwave domain, right, of the spectrum, of electromagnetic spectrum. So I'll talk about qubits and how to manipulate them, not in the context of any of this candidate architecture, but in general, right? Like let's say there is a qubit which is abstract, 0 and 1. How do you manipulate its states? Because how well you manipulate really gives you an idea of how good your quantum computer is. You need to be able to manipulate your qubits extremely well, and if you are able to manipulate your qubits extremely well, you will be able to develop, right, or manufacture a quantum computer that basically outperforms classical computers. So it all comes down to how well you can control your qubit. Okay, so I can give you a little bit of what Google did, right, in 2019, because they basically send ripples across the world by one single experiment. And this was a very carefully designed experiment. And they have this chip, it's called sycamore chip. And they have, I guess, 54 qubits, if I'm not mistaken. One needs to check that, but 54 qubits. And these are all qubits, right? The crosses, gray crosses, they are qubits. And this qubit are coupled to their nearest neighbor, right? So this has 4 nearest neighbor here on the right and on the top, right? And each of these qubits are coupled to its neighbor via this adjustable coupler, right? I guess you can even call it tunable coupler. Because I'm familiar with tunable coupler, but I think that's what they mean. And you can tune how strongly you want to couple these two qubits, right? So that is their topology. 54 qubits, adjustable coupler, and that is the chip on the right. You see, that is the sycamore chip, and that's about I don't know, 20 millimeters, I guess, and you will find this kind of superconducting architecture there somewhere. And so that is just a photograph, right? And this experiment was conducted at Google. I guess they released the paper on 2019, and it was very interesting for all of us, because this was the first time where they demonstrated that you can do a task on quantum computer that classical computer, even supercomputer, cannot do in like years, right? Cannot do in years. So to do this particular task, a powerful supercomputer would take 50 trillion core hours. And my goodness, I mean, you know, I don't know how long that would really take. So core hours is basically a measure of like time, right, multiplied by how many cores you used, right? And versus they did this experiment, they did this computational calculation within a matter of seconds using Google's Sycamore chip, right? And they essentially simulated this kind of circuit. So this is what happens in this sort of chips. So these are different qubits, right? This is just the one area, maybe here, let's say on the center, and these are like 1, 2, 3, 4 qubits connected to the central qubit, and they have this adjustable coupler A, B, C, D, and there are like more of them, right? This is just 4, and there are like more of them, and each of this qubit is mapped onto this timeline. This is qubit 1, qubit 2, qubit 3, qubit 4, qubit 5, right? And you keep going. But here in their paper, they just showed, for an example, right, just this 5 qubits, and they build this circuit. And I'm not again expert, right, in their experiment. I mean, it's them who conducted that, and they published paper where I have skimmed through it briefly, and I see that they work with this kind of circuits, and they apply gates, meaning they manipulate these qubits, right? And there is some randomness there, and to simulate this circuit to get an answer, the desired answer for a supercomputer, it would take 50 trillion core hours. So to simulate this quantum circuit is extremely difficult for a supercomputer, and they could do it in a matter of seconds. Why could they do it in a matter of seconds with good result or good accuracy? I mean, good fidelity, as we call them, because they could manipulate their qubits really well, extremely well. So you essentially need to manipulate one qubit, you know, to how fast can you change the state to 2, or sorry, change the state to 0 from 0 to 1, 1 to 0, create superposition. How fast can you do that? That is called manipulating qubit states and interacting them, right? Again, you need to perform gates on it. So we call qubit manipulation as gate operation, right? You perform gate operation on single qubit, or you perform gate operation on multiple qubit. That is called manipulating qubit. And for single qubit, just one qubit, you can do that by applying microwave pulse, right, through transmission line. It's basically just a pulse, right? Electromagnetic field. And for 2 qubit, you can control it by this kind of step function, right? So you see these 2 qubits are interacting via this gate. So this is like you perform operation on single qubit, square root of W operator, perform operation on single qubit again, square root of X. These are just Pauli operators, right? Square root of X, single qubit operator. And then here, this one is 2 qubit operator. So there is single qubit operator, there is 2 qubit operator, and you can even have multiple qubit operation, right? And it's very important to manipulate single qubits, as well as it's very important to manipulate 2 qubits, right? So that is the whole context of this lecture. I will tell you how to manipulate them. So it all comes down to Bloch sphere. So like classical bit, it lives just on 2-dimensional, so it has 2 degrees of freedom, right? Well, it can be only in 2 states, right? 0 and 1. But the states of qubit, I mean, you can always have 0, 1, 0 and a little bit of 1, 0 and a little more of 1, right? And so on and so forth. So there is this continuum of states you can obtain in quantum computation. And for a single qubit, the state of qubit is entirely defined by all the points on this Bloch sphere. So you start at the origin and you point to a direction that is going to be a state of some state of qubit. You point here, another state. You point here, another state. You point here, another state. And we call that the states of a single qubit lies in Bloch sphere, right? And states of many qubits lies in many Bloch sphere, right? And I will tell you a bit about how, right, one can characterize the states of this qubits on the Bloch sphere. And you can read more on Wikipedia. Wikipedia has a nice article, right, on Bloch sphere. So let's see. Single qubit gates are very simple. I mean, you probably know from your high school, right? They're like 2x2 matrices, which we are familiar with. And there is X gate, there is Y gate, there is Z gate. This is Hadamard gate. This is as phase gate, which adds phase to qubit state. Same here, right? Or which adds like complex amplitude here, which adds phase here. And these are the matrices, right? Very simple. X is just off diagonal, non-zero off diagonal. Y has non-zero off diagonal, but they are imaginary. Z has diagonal elements, off diagonal elements are 0. H is full, all its elements are non-zero, and S is diagonal, and phase T gate diagonal and off diagonals are 0, right? And these are just the quantum logic gate. And one can use these gates to manipulate the states of a single qubit. You can use more of this to manipulate states of more qubits, right? But with just this operation, you cannot interact them. Today, I will tell you just about manipulating single qubit. And so the arbitrary state, it turns out that an arbitrary single qubit state can be written in this form. And this is something I pulled up from the internet. That there is a presentation which I forgot to cite here, but you can very well look this up on the internet, and this is from one of the slides, right? And it turns out that an arbitrary single qubit state can be written like that, right? So you have state 0 plus state 1, and it has some amplitudes, right? And you can tune this amplitude continuously to obtain different states on this Bloch sphere, right? So it's very simple. So there are 2 parameters. This is called global phase. It doesn't have any observable effect, but important parameters are this theta and phi. So just take this as a definition right now. Any arbitrary single qubit state can be written as that. You can write this as either 1 by root 2, 1 by root 2, right? Or I don't know, just 1 by root 4, 3 by root 3 by 4, right? And you can choose theta and phi such that it gives you those different states, right? And theta will be from 0 to pi, and phi will be from 0 to 2 pi. They define a point on a unit 3-dimensional sphere, and that is Bloch sphere, right? So we don't care about this phi, this prefactor, complex prefactor in the beginning, because if you take overlap this with psi and take the absolute value squared, it'll just become 1, right? So we don't care about that because it doesn't have any observable effect. You cannot see that in experiment, right? This global phase, right? Or it is not relevant. And so essentially you're left with just this form with 2 parameters, free parameters that you can tune, right? And what your quantum gate does, or quantum computer does, is it tunes these parameters in the course of information processing. Okay, now, so let me start by talking about spherical coordinates because they're related. So you can write your Cartesian coordinate in terms of polar coordinates for a sphere like this, right? So x will be r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta, right? And radius is 1 for us because in the course of this computation, coherent computation, the radius should remain 1, right? And that's important. So unitary operations, they preserve the norm. We call it that the unitary operation preserves the norm. So we set R to be 1, right? And that comes from normalizing. We call it normalizing. And you can write any state in this way, like real and complex part, if you like, and you end up with something like this, right? And now this is funny, right? Because how do you reach at this state 0? Because you also have to reach state 0, right? This is a space in Bloch sphere. There is 0, there's 1, and there's different combinations of 0 and 1. But what value of theta is going to give you just state 0? Can anybody answer? So what value of theta is going to give you just 0? What is cos 0? It's 1, right? And sine 0 is 0, right? So if theta is 0, you're going to get ground state 0, right? Now, what if theta is pi by 2? If theta is pi by 2, this is going to be 0, and this is going to be ei phi 1, right? So you can choose this and create ground state or excited state, and that is what quantum operation does. It plays with these different parameters and gives you a final state, right? And we'll see this more when I demonstrate quantum operations on QDIP. So we have 2 adjustable parameters, right? And they are lying this state, they lie on Bloch sphere. Now, so we saw that you can write Bloch sphere in this manner. So you can, with this mapping, you can get all the points on upper and lower hemisphere. And so this range, theta from 0 to pi and phi from 0 to 2 pi, are going to define all possible states of qubit, and these states lie on Bloch sphere entirely, right? And I would say that is the message which I'm to send across. So if you parameterize your general state like this with cos theta by 2, 0 to ei phi sine theta by 2, 1, right? So this is enough to obtain all possible states on Bloch sphere, right? So now what are rotations, right? So basically, and I'm talking single qubit rotations. So X, Y, and Z matrices are Pauli operators, and these Pauli operators generate rotations, right? So these are unitary, meaning if you apply them twice, they're going to give you identity. They're going to give you 1, right? And they're invertible, because quantum operation, you perform operation forward in time, right? And you should also be able to perform the operation backward in time, right? So they are invertible, and it rotates Bloch sphere, Bloch vector, right, about x, y, and z axis. So Pauli x gate rotates your Bloch vector about x axis, right? Y, Pauli y gate rotates your vector around y axis, and Pauli z gate rotates your Bloch vector around z axis, right? So that's z, there is x, and there is y right here. So you rotate the vector around those axes. But now you see the problem is x, y, and z are matrices, and you cannot just simply exponentiate the matrix, right? Because it's not that easy. You need to keep in mind their non-commutative behaviors and so on and so forth. But mathematicians slash physicists, they have discovered an intelligent way to evaluate exponential of an operator. And how do you do that? You do that by using Baker-Campbell-Hausdorff formula, right? So it's a little bit math. So what you do is you basically expand that in Taylor series, right? Some sort of Taylor series, I guess, and you end up with this combination of elements, and you can reorder them in this way. Again, this is from PDF I found on the internet. Forgot to cite that. You can look it up by typing this text and putting it in inverted quotes. The Google will give you out. And at the end, after this rearrangement, you reach at this very simple expression for exponential of matrix. And you reach at this simple expression because of the fact that Pauli matrices has this property: x squared equals y squared equals z squared is I, which is identity. So we can use this equation to evaluate the rotation operators, right? So that is going to be your rotation operator that you will use to perform computation on a qubit. Anybody has any question at this point? Okay, great. I hope I'm not making it too complicated. Quantum computing is difficult, so one needs to get used to it more. But we'll get there. Don't worry. But these are just some basic fundamental things that you need to learn. I mean, a lot of it is math, and I guess that is what you have to learn. And it's important for quantum computing. It's a lot of math. Now, so the rotation operator becomes something like this. So there is minus I, and it's very simple to treat minus I. You just put minus here, and you obtain this thing, right? So E minus I theta x by 2 is cos of this and then sine of that. And then, yeah, this can be written like that, right? And because x is 0, 1, 1, 0 of diagonals. And similarly, you can write rotation around y-axis in this form and rotation around z-axis in this form. So this matrices entirely generate rotation around all three axes of your Bloch sphere. And this is very handy, right? Because in the course of computation, if you apply this kind of operations, they will put your initial state in different positions in this Bloch sphere, right? So we can do a small, I guess, example to see what happens if you rotate around, let's say, by theta equals pi. Let's see. So let us rotate around x-axis by theta equals pi. So this is the matrix. You substitute theta equals pi here. What will you end up with? You'll end up with this very simple expression: 0 minus I 0. Now you can pull this minus I out because I mean, this is just a global phase, right? And like I said, if there is a phase which is global, which is like outside, right? It doesn't matter. So you can think of it as just being X gate. So this is a pi pulse. We call it pi pulse in quantum computing. It takes your state 0 to 1 and 1 to 0 because it has this off diagonal terms. If you multiply 0, 1, 1, 0 by 1, 0, which is a vector, matrix 0, 1, 1, 0 by 1, 0, you'll get 0, 1. Similarly, if you multiply that by 0, 1, you'll get 1, 0. So it changes from 0 to 1, 0 state to 1 state, and 1 state to 0 state. And that is very handy in quantum computation, right? So it rotates by 180 degree about x-axis. And that is called pi pulse in quantum computation. So you see, these are like different axes: z-axis, y-axis, x-axis. And if you rotate this 0 around x-axis, you rotate like this, like this, like this, like this, or by 180 degree, and you get this. You end up in this 1 state, right? So and this axis, right? It has like two sides. This side, let's say, so to speak, positive side and negative side, and each of the side is defined by the superposition, and y-axis is defined by the superposition with complex amplitude, right? And I will teach you a little bit about how to, let's play with this, right, on QTIP. I'll tell you what happens if you perform different operations. Give me a second. Let me perform. Yeah, okay. Yeah, so let me start QTIP. Okay. Go, yeah. Sorry. Yeah, I should have put this already. Users. So we have, I want to open my QTIP program, codes, open in your terminal at a folder. So now let me, no, sorry. So, yeah, I use Anaconda to do my Python scripting QTIP environment, right? So now I will start my Jupyter notebook, which is a tool, right, to interfaces with Python programming language, and you can write it as you would write in Mathematica, for example. It is quite handy. Notebook. So it opens Jupyter notebook. Can you still see?
Yes, we can.
Okay, great, great. Thank you for the feedback. So now have a look here. What I will do is, it's a QTIP is a library. If you use Python, you can just export it as a library. But first, you need to install this library. It's called QTIP, and it's this one very, very popular, and we use it all the time in our lab at a company, at my company. And for example, you can say, okay, let's import. Let us import right now. Okay. Yeah. Sorry. I want to import all the modules, right? So you should say from QTIP import star. It imports all the functionalities of QTIP, and let us import numpy also, right? And with numpy we get like functions, right? Like cos theta, sin theta, whatever. Now on QTIP you can build Bloch sphere by just giving this command, right? And you can even show Bloch sphere. Have a look. That's Bloch sphere, right? So it has x degrees, y degrees, and z degrees. And z's, so these are poles, 0 state and 1 state, and x will be superposition of 0 state and 1 state, and y will be again superposition of 0 state and 1 state, right? Now what I can do is now I can manipulate the states, right? Let us first define a state. I'm going to define state, or let us plot some vectors, right? Let's say vector 0, 0, 1, and let us say b. If you do b, add vector VC, and if you say b dot show, look, it adds a vector, right? It added a vector on the north pole. So x, y, z, right? So this is again simple math. Now let us add basis state set, right? So down or down is, so what is basis set? So if you do basis 2, 1, what this means is you are giving your computer, you're asking a computer to give you out state. So, okay, let me say that again. Basis 2, 1 is a command that defines your computational state of qubit, right? So 2, 0 is up state and 2, 1 is down state. You're saying there are two states, and this is saying which of the two states do you want to spit out, right? So 2, 1 is going to spit out the down state. Let us add that too. Let us add that as a vector now. Yeah, so b dot vectors down, right? Now b dot so will give you okay, so that did not work. Sorry, I think I should write states. Yeah, I forgot. I don't need this Bloch sphere, you know, so I don't use this too much. This is 2, 1. Yeah, so there is some problem. I don't know why. Index b dot show b dot add states. This is kind of weird. Okay, that worked, I guess. Add vectors. Yeah, I don't know what happened. Let me see. And that works. That works. Yeah, that works. All right. I don't know what happened, but you see, you define down state, which is basis 2, 1. It gives you down state, right? If you do up state, it goes to 0, right? So now b dot add states up b dot, right? So it added the up state too, which is blue, right? Now we can manipulate that, right? So what do I have here? I've chosen some commands to do that. Now I told you, right? Sigma x is the one that changes your state from 0 to 1, right? So now we can bring, let's call it so up. Now down is going to, you obtain down by applying sigma x operator to this up state, right? X up will give you down state. You see, 0, 1. Now what was down state? 2, 0. What's upstate? Upstate is 1, 0, right? Now down, this is sigma x times up gives you downstate 0, 1. And upstate is 1, 0, right? Now let us apply sigma x. Up twice. Those still give you upstate, because like I said, if you concatenate sigma x twice, it's going to give you unity, which does nothing, right? And that is good. So I guess this is a very simple example. I mean, we are sort of out of time right now, and I have some announcement to make too. But I recommend you guys play with that. You can also apply, I don't know, sigma z to up. What happens there? Nothing. If you apply sigma z to down, it'll give you -1, right? Because there is this sort of form here for sigma z. Z1, there is -1, right? It just adds like minus to the excited state. And this QTIP is quite insightful and very handy. I don't play with Bloch sphere, but I do more complicated computation with QTIP, but you guys can play with that. I think it's very interesting. But you need a Python, and you just need to import this library from the website. It's very simple. Yeah, so that was basically it from the tutorial side. I will teach you more of this sort of programming in the future, and we'll have some more fun with more programming like that. And yeah, visit us at onequantum.org, and there is a cocktail party in a few minutes where we can like network, right? I want to announce something that so this is feedback from Hobbyskar, and he suggested, if there could be projects, right, where you guys can work like more handedly. And I would recommend, so Hobbyskar, he has been kind enough to build a little community, I guess. I don't know where he wants to do it, maybe on Slack or something like that. I would recommend you guys team up, and this is all voluntary, right? You're free to do it or not, but if you form a team, you can just reach me out, and I can provide you with some projects, really small calculations, quantum computing calculations. And there will be also some opportunities for hackathon once you guys get good at it, right? And we have a platform on StrangeWorks where we can do this sort of programming. And yeah, feel free, I would say. So, okay, there are some questions. Yeah, Aviskar says, which architecture is the most useful, trapped ions and silicon quantum dots? Trapped ion is most popular, more popular than silicon. And Aviskar, you are going to maybe initiate, I guess, this project thing.
Sure.
Okay. So yeah, I mean, he will probably send you guys an email, and I think it's very interesting. I was very happy when he first told me that he wants to do projects, and it'll be very super useful and interesting for you guys too. And I recommend that. Okay. Yes, I can share the slide, Roshan. Now that is pretty much it for today. And next week I will teach you some more of these quantum operations, and we'll be very happy to see you guys again. So thank you for joining. There is a cocktail party, don't forget. You just need to click here, and I'll be there, and we can meet once more there. Thank you all, and have a nice day. I will stop recording for now.